Hello, my name is Juha Hukkanen, and I believe I have made a couple of really important inventions. First, 1.5 years ago, I received a patent for heat engine system that can obtain electricity from small temperature differences with over 90% thermal efficiency. You probably are so wise that you know that it should not be possible, and you know that it would be enormous violation against the Carnot's theorem. Let's see here, Carnot's theorem. It says that no device converting heat into mechanical energy, regardless of its construction, can exceed this Carnot's efficiency. And this the claim that small temperature differences can be converted with over 90% efficiency, that should not be possible. You probably also know that the Carnot's maximum efficiency for systems can be calculated using this kind of equation where 1 minus the cold reservoir divided by the hot reservoir temperature in absolute Kelvin degrees. And an example here, what I will be using in this presentation is here that I will be using this kind of numbers a lot. So when you calculate 1 minus 294 kelvins divided by 1089 kelvins, you get a maximum efficiency of 73%. So what the patent I got was basically impossible according to this Carnot's theorem, but it is not, because I have found, and I can prove it with many decimals accuracy and in many ways, that it is the pressures at the heat engine's entry and exit side that determines maximum efficiency. And this opens for door for making heat engine systems that have much above the Carnot's efficiency. So I will be showing you this, and let's see first. Here is the patent I got. So this is a basic system, extremely simple. I will be going through that in a small, very soon. And let's have a look at why the Carnot's theorem is kind of failing. It's not about the entry and exit side temperatures, but it is about the pressures. And I don't blink. I will show you this very exactly now, and you can calculate those how many times you like, but so it is. So if we have here this kind of a system, a box and a pipe, and in a pipe we have a heat engine and a generator that's removing the energy from this system. Initially we have 294 kelvins both outside and inside, outside of the system and inside of this 1 cubic meter cube. And we have also 101 kilopascals pressure outside of the system and inside this cube. So basically the whole system is initially at rest. Both sides have equal temperatures, equal pressures. And then we heat this thing. We can use external heating so that we suddenly get the temperature of this inside of this box to be elevated to 1089 kelvins. That's the same kelvins that were in that Wikipedia page also, 1089 kelvins. And the outside temperature remains 294 kelvins. So we can calculate that, let's see, we can calculate this Carnot efficiency as was shown in that Wikipedia article like this. Yes, and we go back. So we get this 73% maximum efficiency for this kind of a heat engine. That's obviously when this contents of this box get heated, the pressure inside of this box will rise from 101 kilopascals to 374 kilopascals. And that I can calculate. I'll show you exactly how that calculation goes. And it goes like this. So let's we have this. I recommend you use this calculator. So as we know the pressure, that will be it is the initial pressure in that box was 101 kilopascals. We had the volume 1 and we had 294 kelvins. And we calculate that initially that box had this much substance, 41 moles. Then we calculate we know that we have this amount of substance. We have the volume 1 cubic meter. We have the new temperature 1089 kelvins, and we get the pressure, and it's 374.1. Yes, and that is the elevated pressure after when this has been heated. So when we have this pressure here, the outside pressure was this much lower. Then what happens when we remove 73% of this pressure? And we can calculate it like this, and we get the outside pressure, 101 kilopascals. When we remove 73% from this 374 kilopascals, we get the outside pressure. So basically, this means that this heat engine can, when operating with maximum efficiency, lower this pressure coming from the entry side to the level of exit side's pressure. And at that point when there are equal pressure kind of from both sides, then obviously the system cannot take any more energy. It kind of stops then. And when we have this pressure, we know the pressure, and we can calculate the pressure force if we know the cross-sectional area of this pipe, and we can calculate that using this kind of a formula. So we assume that our pipe's cross-section was 0.1 square meters. Then we get this pressure force to be 37.4 kilonewtons. And the pressure force coming from outside, that is pressing the heat engine from this side, can be again calculated to be 10.1 kilonewtons. And when we remove 73%, that is that Carnot's efficiency, from the pressure force coming from the entry side, we get the exit side's pressure force. So we are here dealing with unavoidable Newtonian forces that are determining the Carnot's efficiency, actually. So the idea that the temperatures would have some kind of defining significance for heat engines' maximum efficiency is kind of unavoidably bound to the Newtonian forces using this kind of equation. So, and then we think about another case. Now, previously we heated this anthracite box to 1089 in order to get this higher pressure. But what if we had here a container with pressurized air, and that pressurized air would have been at a lower temperature than the outside air? It would just create this pressure 374 when that valve of that compressed air container would be opened. It would be the colder gas, but it would still have that pressure, and as it would have that pressure, it would have these Newtonian forces exactly the same way, and it would again have a 73% maximum efficiency, even if it would be at a colder temperature than the outside air. So this is a kind of a unavoidable demonstration that the temperatures are not the ones that are defined the heat engine's maximum efficiency. All heat engines are actually pressure engines, as I will be showing. And this has been also demonstrated, that the cold can, it doesn't need to be hot. It has been demonstrated using an experiment. Let's see here. Zheng and Zhu at the Wuhan University of Technology did show, for example, this a performance analysis of four-stroke compressed air engine. So they were powering a four-stroke engine with compressed air, and they observed that when they have higher pressure, it will have more effective power. It will create more power when the supply pressure is higher. But they also demonstrated that at the different supply temperatures, there was the colder was actually a little bit more efficient at different at the same pressure, but a little bit colder was actually performing a little bit better, and they did at different speeds. So, but so they concluded also that compared with other parameters, supply pressure has a greater influence on the performance of compressed air engine. And the increase of the supply pressure can effectively improve the indicated work and work efficiency. So, the supply temperature has little effect on the performance of the compressed air engine, with the increasing supply temperature, the average effective torque, effective power, and work efficiency will decrease slightly. So it's not the heating, the temperature of that gas that would be kind of improving. It was actually decreasing, and the pressure did the trick, so to say. So this is kind of a very important observation for these inventions. It is the pressures that power the heat engines. And another vital thing for this invention is the realization that when one cools condensed vapor, so that there's a little bit of vapor, there's a little bit of liquid. When such container with vapor gets cooled below the liquid's boiling temperature, its pressure will decrease enormously. And we can have a video that will kind of nicely demonstrate that. Okay, so here we have a school demonstration. They have a little bit of boiling water inside this barrel, and the water vapor has filled this entire container now, and there is the same pressure outside and inside of this barrel initially. So here this Mr. Getchu's Geography channel next shows that what happens when they close the lid and they remove these gas burners that have been heating this barrel. So next, the teacher will be cooling this barrel that is now totally closed, and as he begins to cool, that temperature inside of this barrel with its vapor will decrease. Now let's say it may be something like 370, 360 degrees Kelvin, like 90 degrees Celsius, and it's very small amount of energy that gets removed from this barrel, and small amount of energy was removed, but the pressure effect of that small amount of energy was enormous. And so the temperature of this inside of this barrel can only be something like, maybe it's like 60, 70 degrees Celsius, only 20, 40 degrees below the boiling temperature, but its volume has totally been lowered to a fraction of what it was a minute ago. So as we can see, lowering of the temperature of vapor so that it goes below the boiling temperature will enormously strongly lower the pressure, and here we have that pressure difference causing irreversible deformation of this strong metal structure. And let's again look here. If we had only gas in that school classes barrel, if the barrel would have contained only idle gas, and we would have cooled it from 100 degrees Celsius to 80 degrees Celsius. Well, we would lower 20 degrees the temperature of it. The volume of that, of the pressure of that inside that barrel would have only been lowered by 5.36. That's kind of exactly according to this Carnot's rule. So 5.36% would have been the reduction of this pressure. You can also see that. So this is kind of this with ideal gas containing container barrel. The pressure decrease would go a straight line towards absolute zero temperature. But when we had a vapor, so that 20 degrees reduction did cause the pressure reduction to be greater than 50%. So that is why that barrel was imploding with that little bit of cooling it received. So this is a very, very important other part of this invention. First part is that the idea that it's the pressures at the heat engine's entry and exit side that are determining its maximum efficiency. And this way, when we have at the closed space vapor that gets cooled below that liquid's boiling temperature, we get a non-linear reduction. We get a very much stronger non-linear reduction in pressure. And we know that, and actually I will show you soon that these pressures are the ones that drive this heat engine. So this is the way we get that pressure difference that we will be using and obtaining that very large, over 90% thermal efficiency. So let's next look at that proof that I have for making the claim that the pressure difference between the heat engine's entry and the pressures at the heat engine's entry side and exit sides are what are really determining its maximum efficiency. So let's dive into that theory next. Now we need to discover a new equation that would explain the good results that Carnot's theorem has been providing during the past 200 years. And we need to have a better equation such that it would also explain this effect of pressures, because as we saw here, it was not the temperatures that determine the maximum efficiency, because a lower temperature can also produce an equivalent maximum efficiency based on these pressures and pressure forces. And I have found that the new equation, it's kind of a surprisingly similar to that Carnot's equation, but the new equation looks like this, actually. So it's 1 minus P pressure of the exit side divided by pressure of the entry side, while the Carnot's was temperature of the cold side, that's the, and divided by temperature of the outside. So, and to prove that this new equation really works, I have used several evidence systems, and of which this one is probably the most clearest. And this evidence system does provide the proof that we can obtain the same Carnot efficiency values with multi-decimal precision also from pressures and not just those temperatures that Carnot is using. So in this evidence system, we have two cubes, 1 cubic meter cubes. We assume that they both contain 1 mole of ideal gas, and they are initially at the same temperature. Then we change temperature of one of these. We can heat one of these, or we can cool the other one, so that they will be pressure difference inside. These boxes will have different pressures. So if we have that, we already know that if we have the hot side temperature of 1089 kelvins and the cold side temperature 294 kelvins, then the maximum efficiency will be 73%, 73,003 actually. So I have calculated these. When we know these volumes of these boxes, we know the amount of substance in these, we know the initial temperature, which would be 294 kelvins in both of these boxes. These boxes would be connected using a pipe that contains a heat engine. So initially, both systems have 294 kelvins, 1 cubic meter, 1 mole of gas. Then we heat this hot entry side box to 1089 kelvins, and we calculate the pressure in this box then. And we can also calculate the pressure in this box that would remain cold. And the pressures calculated using the ideal gas equation for the exit side 2444 pascals, and for the entry side 9054 pascals. And if we use this equation that I have discovered, we get the exactly same Carnot efficiency value that we would be getting using only the temperatures. So it seems like the pressures of the entry and exit side are able to provide same numbers, and I have tested this with the wide range of temperature combinations for which all I have calculated the Carnot's efficiency value using the cold and hot side temperatures. For example, if we have here hot side 600 kelvins, cold side 300 kelvins, we get the maximum efficiency from this equation, 1 minus 300 divided by 600. So it's 0.5, that means 50% maximum efficiency. And we get when we calculate the pressures, then the hot entry side's pressure would be 4.9887, and the exit side's pressure would be this much, and we get again the same efficiency. And so this is for all temperatures, we get the same numbers from pressures. And how do we explain that? Well, the explanation is quite simple. It's here in this my small article that I put online a couple of years ago. Kind of, it has been there quite silently, but it has been there. And it's let's see here. The explanation is in the table. Here it is. So what really are the components of pressure? So if we need entry side's pressure and exit side's pressure, now we need to think, where does that pressure come from? And as I mentioned, I used the ideal gas equation, and it worked perfectly for explaining the temperature, this Carnot's efficiency values. But how does it work? Well, it works because the components of pressure are mostly same at both the entry and exit side. For example, if we have unlimited volume on both sides, then we can, and both entry and exit sides, then we can remove this from this equation. If the heat entry is not leaking substance, so the same substance that is part of the pressure reformation entry side will be part of the exit side, then that's, again, we remove that. The R value, gas constant, if the substance remains the same, then we can remove also that from the equation. And the only variable left will be the temperatures. So the pressures are kind of hidden from this. If the substance is not missing, the volumes are unlimited on both entry and exit sides, and substance doesn't change. So the only thing only difference that will manifest then will be the temperatures, the entry side temperature and exit side temperature, or as Carnot put it, that would be the cold reservoir temperature and hot reservoir temperature. So this is why it works for. But also you should notice that when we are in this invention now, when we are dealing with the system in which vapor gets condensed into liquid, then and the liquid gets cooled, it does not maintain that gas constant. It's the substance, nature of substance changes, and you can see that very clearly in this. And the pressure reduction when you cool certain gaseous gas, when you cool it towards absolute zero, so the pressure decrease will be a linear line that goes straight towards the absolute zero, while the vapor that gets condensed into liquid, it will form its pressure decrease is non-linear. It's very rapid and non-linear. So when ideal gases follow this line, this doesn't. When there's a vapor that's condensing, and as that the vapor's pressure goes down so very rapidly, very strongly, so we can get with a small amount of where we only need to remove very small amounts of heat from the liquid or the condensed vapor, so that we can get this enormous drop in pressure. We get the pressure near zero, and if we had only gaseous gas, we would need to lower the pressure, lower the temperature by a couple 100 degrees more in order to achieve similar pressure reductions. So if the heat engine's maximum efficiency is really dependent on pressures, and we get this pressure difference by cooling the vapor below its boiling temperature, then we can overcome this Carnot's temperature-related rule, because of this nature of the substance changes in our favor, so to say. So there are many different evidence systems in this article. Heat engines are powered by pressure and heat, and these evidence systems, for example, they show that first here is this known relationship between maximum efficiency and the cold exit side temperature. So it has always been known that if the cold exit side's temperature is 0 Kelvin, the maximum efficiency of such system would be 100%. And you get that from, for example, if you calculate here 1 minus 0 Kelvin divided by non-zero Kelvin, so you get that 1.00, meaning 100% efficiency. So the colder you have been able to get the exit side, the higher the maximum efficiency has always been known to be. And here I somewhere also calculate this for similarly for pressures that are in this similar curve. Let's see the bits of blue lines there. Yes, so I show that the same maximum efficiency when the exit side's pressure goes to 0, and we can get that exit side's pressure to very, very low when we have cooled the liquid that has gone to the exit side. When we have cooled that to near to the freezing temperature, then we will not have much partial pressure of that vapor left. So we can actually see that here. Let's see. Okay, so we have that here. Yeah. And here. And if we go to, so, okay, so here. Yes, here it shows how in normal atmospheric pressure, when you have at the 100 degrees, you have 101 kilopascals, and then when you go to near 0 degrees Celsius, 273 Kelvin, you will only have less than 1% of that pressure remaining. So the pressure difference will be like pretty enormous that way. And it's not just water, because you can also use many different substances. They all behave pretty much the same way. Let's see here. Okay, so here we have water like that enormously strongly vapor pressure lowering curve, and they are all these other substances behave pretty much the same way, so that as you go towards the freezing temperatures, then you will have a very low partial vapor pressure of that substance. So it's not just water. So this is kind of important, and I do show here in this article that the effects of and kind of not limited to this explaining with this gas constants difference, but I also test the changing volumes at the entry and exit side, how they impact the maximum efficiency. Also discuss the leaking of substance, and I show that it really is the pressures using, let's see, here we have something interesting. So let's see here. There's an evidence system like that, looks like this. This kind of shows very clearly that it must be the pressures that are defining or it cannot be the temperatures, at least. So if we have here two identical automobiles, and the entry side in temperature in both of these is 1089 kelvins, and the outside air pressure is 1 bar, 101 kilopascals, and the same exhaust gases are also pushed to what that's atmospheric air, it's the same 101 kilopascals. The temperatures, if we assume that the temperature of air, ambient air, is 294 kelvins, then our maximum efficiency for this automobile would be 73%. So if it would be consuming all the motive power generated by this engine, heat engine here, for turning this wheel, so it would be able to achieve a maximum of 73% maximum efficiency. But the second car is that's a little bit different thing. So here we have an identical automobile, atmospheric pressure is the same, but this car does push those exhaust gases deep into water, 10 meters deep into water. So there will be double the pressure that exists here at the exit side. The temperature of the water would be the same. So we have the same temperature, 294 kelvins, and we can assume that the water is also 294 kelvins. So if the Carnot's theorem would be used for calculating this maximum efficiency, we would again get that 73% maximum efficiency. But because you need to consume lots of energy for overcoming the hydrostatic pressure that is caused by this pillar of water here. So you will need to consume energy for pushing these exhaust gases into water, and that's kind of not free. You need to consume certain amount of energy. So if you would be able to achieve this 73% efficiency also for this automobile that is pushing the gases into water, then this automobile would need to create energy out of thin air, and that would be very much in violation of everything. So it cannot be 73%, and instead I calculate using these my equations, that's using the pressures. I get this calculated. Let's see here. It is there. This automobile B that was pushing the gases into water, it would have a maximum efficiency when it's pushing those 10 meters in the water would be, the maximum efficiency would be 46%. And I also calculate the maximum depth that automobiles would be able to push those exhaust gases, and that maximum depth would be 27.04 meters. That consists, so that would be causing the exhaust gas pressure at the exit side to be 374.1 kilopascals. And as we can remember clearly, we have already calculated that here. So if we have the entry side temperature at 1089 kelvins, and we get that 374 kilopascals pressure from by this heating. So we, in this case, when we have the air pressure of air is 101 kilopascals, and then we have this hydrostatic pressure, then together those at the depth of 27.04 meters will cause this pressure of the exit side. And in that case, when the exit side's pressure is equal to the entry side's pressure, the maximum efficiency will reach 0. If we would have calculated the maximum efficiency for just using the Carnot's equation, when we know that the temperature of air and temperature of water would be the same, so 294, we would in all cases get this 73% maximum efficiency. So I conclude that, and I prove it in quite many ways here, that heat engines are powered by pressure, pressures of entries and exit sides pressures, not the temperatures. And the correct equation is for calculating the heat engine's maximum efficiency is this, and the heat engines themselves are not actually heat engines at all. They are all pressure engines. And okay, so that's kind of a important theory. Now we need to also take a look at, here is a theory part that's interesting and important for understanding the innovation. So we have in this kind of a system, again, that when we have heated this to this box to 1089 kelvins, we get, and we have that 1 mole of gas and 1 cubic meters. Our pressure would be this, and the exit side's pressure from 294 kelvins, 1 mole of gas, 1 cubic meter, it would be to this. So if we have 2 heat engines in this system, and the first one is maximally efficient, achieving 73% efficiency, then this first heat engine will be able to lower the entry side's pressure to the level that exists at the exit side. And therefore, the second heat engines would have both and at its entry and exit side the same pressures, and therefore it would not be able to take any more energy from this system. And if we then instead would have a non-optimally efficient Carnot's heat engine in this tube as a first heat engine, and so that this heat engine would only take 33%. So the second heat engine would still be able to obtain 40% of this total available energy. Total available energy would be that 73%. So we can calculate that again using this. We know that if we have that 33% efficiency, so the pressure drop caused by this first heat engine can be calculated from this equation. We just simply remove 33% of that pressure, and the pressure after this first heat engine would be 6.06 kilopascals. We also can calculate that using newtons. So, and when for the second heat engine, we have the entry side pressure, that is what was left from this first, after this first heat engine. So entry side pressure is 6.06 kilopascals, exit sides 2.44. And then we can, when it's working maximally efficient, we can get this 40% of the total energy removed. And the maximum efficiency of this second heat engine would actually be 59.7, and that can be calculated from this equation that I showed in my article. And it's from this equation. So 1 minus 2.44 divided by 6.06, and you get that right side maximum, the right side heat engine's maximum efficiency calculated. So as long as there exists a pressure difference at the heat engine's entry and exit side, you can basically obtain more energy from the system by placing successive heat engines after that. So as long as there is this pressure difference available. Obviously, the less the pressure difference is, the more difficult it is to obtain energy with from the system. So if there is a very small pressure difference at the different sites, so it's difficult to extract energy from that. But when we have in let's say here, in this kind of a system, we can have an enormous pressure difference. So if we have like 5 kilopascals, now we have had 50 kilos, but if we cool that liquid near the freezing temperature, so the partial pressure on this side will be kind of, let's say, 5 kilopascals. So the pressure difference is very very great. You can calculate the maximum efficiency for this. That the pressure difference between the different sides of this heat engine from equation 1 minus 5 divided by 100. So it's we will have lots of power you can extract using ordinary turbine or piston engine. So let's continue here a little bit more. If we had again no pressure, no temperature differences, but that initially we would have the same kind of temperature in both, so we would have Carnot efficiency of 0. And what's to highlight the importance of this pressures versus temperatures in defining the maximum efficiency. So if we, as we had in that patent picture, this one, okay, so we had only the entry side temperature of 308 kelvins and the exit side temperature of 298 kelvins. So if we calculate from those numbers the maximum efficiency, then the maximum efficiency of such Carnot heat engine would be 3.25 percentages. That would be totally ridiculously small, but because we get that enormous pressure difference and the heat engine's maximum efficiency is really coming from those enter and exit side pressures, then we can have much higher maximum efficiency. So let's talk a little bit about what kind of heat engines does this invention apply. The previous patent was mostly for obtaining energy from low-grade heat coming from the environment. And now that we know that it is the pressures, we have shown that kind of clearly with the theory that pressures on the different sides of a heat engine that are powering, then we can assume we can use any kind of heat engine here. We could have turbine or piston engines, but now we are to make things clearer, so we just replace this heat engine with the metal plate that we will be doing. It's a machine, metal deforming machine, let's say, and that will be our heat engine now because it's the pressure engines really. So in this new patent application, the heat will be obtained from energy-rich fuels and be applied for vehicles, ships, airplanes, power plants, nuclear power plants, all kinds of funny things. So the pressure difference that we will be getting is the important thing. So if we are boiling here water and we are have this heat pipe here, so we get this water boiling at 308 kelvins. On this side, it will be causing this 100 kilopascals partial pressure. On this side, we will be cooling it, and we can assume that we cool it 10 degrees below the boiling temperature. If the boiling temperature was 308 degrees, by cooling this side's liquid to 298 kelvins, 10 degrees below boiling temperature, we will be getting this 50 kilopascals partial pressure here, lower than that actually. So if we have this 50 kilopascals on this side, 100 kilopascals on this side, the difference will be 50 kilopascals, and that will be equivalent of having, if we have this cross-sectional area of 1 square meter, that 50 kilopascals partial pressure will be equivalent of having 5,000 kilograms weight placed on a surface that's 1 square meter area. So if you imagine placing 5 ordinary automobiles on a 1 square meters area, that will be crushing this metal. Yes, and the important thing is here that to realize that we really need to cool this exit side's liquid below the boiling temperature. If we don't do that, if we just kind of leave it at the boiling temperature, like here we have only cooled it by 1 degree, so we will be having very minimal pressure difference here, and that won't cause much harm to this metal deforming the metal plate. Our metal deforming machine will not be able to obtain work from that pressure difference. But if we have higher pressure difference, we get much more work done to this thing. So if we have, as we have potential to lower this side's temperature even more, if we lower it to near freezing temperatures like 274 kelvins, we might be getting something like 1 to 3 kilopascals partial pressure on this side. then the pressure difference will be almost 100 kilopascal, and it would be equivalent of having 10,000 kilograms weight placed on a 1 square meter surface. So as we can see, it's a very, very cheap way for making this machine to work much more work. And as we are boiling here water, and if we had that, let's see here, if we have here this kind of a turbine, and it will be the pressure wave will be moving along this pipe, then each meter it's kind of pushing this 50 kilonewtons net force will be creating it will be doing lots of work. It's a 50 kilo joules work for each meter. It's pushing this to this side, and how much liquid can be moved from this side to this side. Well, heat pipes can work with megawatt scale, so there are applications planned where let's say here where heat pipes will be cooling those planned small nuclear reactors, and it has been kind of researched quite intensively that what kind of how much power can be obtained, cooling power can be obtained, can be available by using heat pipes, and here Los Alamos National Laboratories have been, for example, investigating this. And let's see if we have those pictures here, and this is kind of a one way to look at this heat pipe. So we have this kind of a wrongly directed. It says that it kind of goes down, but it usually goes up because it goes much better. Heat, they are cooling so that heat comes from below and goes up most often. So so we will be heating in this here, and the vapor will be going here, and then the capillary forces will be driving this liquid back up here to be heated, and it will be releasing lots of heat here then. So it's kind of a thermosiphon. This is kind of a more normal, let's see, more normal way to operate this. So you supply heat, vapor goes here, heat will be extracted somewhere, and the liquid, as the heat gets extracted away from this system, it will be losing this heat of vaporization, and it will be condensing, and it will be going back through the sides. But often this can be also made so that it's a kind of a circular loop thermosiphon system, so that you heat it here, and the kind of the liquid kind of circulates this thing. So we can have this paper by the National Laboratories of Los Alamos. They are planning to have this kind of a cooling system for those nuclear reactors. They are investigating this. So there are heat pipes that kind of, and there are fuel pins that release heat, and it needs to be cooled then. So heat pipes kind of lifted here, and there's some kind of a heat exchanger that will be carrying the heat then away. And these can operate with multi-megawatt efficiencies. And what's kind of more interesting even is that these can be quite big. Let's see, here in this paper they show those limits that the heat pipes can have. So there are different limitations, what kind of limitations these heat pipes naturally have, but basically they can be built big and have those megawatt scale sizing. So idea is that it does not need to be it may not be boiling the whole liquid, and it must be kind of a liquid that's going one direction should not be kind of interacting with the liquid that's going vapor that's going to the opposite direction, and the sonic limit is 1 because molecules will travel at the speed of sound, and the capillary must have enough capacity to kind of transmit this. And there was some other limit, but the heat pipes can be big, and they can look like these thermosiphons. So if we can have like megawatt size that we push 1 million joules of heat into the system, and in 1 second, and we get that removed from the other side. So these are very effective things. So let's look here again. Yeah. So and the important thing to notice is that it's very cheap to lower this exit sites temperature. And yeah. And again, here we see that we can get, when we lower that exit site temperature, we can get the exit site's pressure near 0 if we go to the freezing temperature or that low. So, and again, as we now know that it's the pressures that drive the heat engines. So just if we have 3 blade rows in this turbine that operate with each with 2% efficiency, take 2% of the energy that's in the fluid, and so it will be removing a little bit less and less of the total internal energy, but they will be going above the Carnot's temperature-based limit, which for this kind of a system would be only 3.2%. But then there's again this, that if we have only a very small temperature difference, like here's 1 temperature decrease, so the pressure difference will be small, and each of these similar turbine blades would be removing very little energy from this system. So, and we can increase the amount of energy obtained from this system by putting more turbine blades here, so that even if this first were able to take only 5%, but if we just have enormous amount of those turbine blade rows, they will be collecting the whole 98% for that of this, and 2% will only need to be going here. But again, if we have very small temperature differences, we will be not, if we are not cooling it enough for below the boiling temperature, then we will be having very small pressure difference. We'll be obtaining minimal amounts of of energy, even if we have those great numbers of turbine blade throws. So now it's important to notice that these existing technologies that operate with a lousy thermal efficiency, they all follow the Carnot's theorem pretty much, because they don't lower the temperature below the boiling temperature when it's kind of it has done the work to the turbine. So instead, for example, here we have kind of a two-flow turbine rotor. So when usually in all those steam turbines, the gas gets expanded to create the. So here it's kind of the gas gets inserted in the middle, and then it's going to both directions, to both of these rotors, and you see how these blade rows then are expanding, are getting bigger and bigger, and the gas will be drawn to a greater and greater volume, and is doubling of the volume will reduce the pressure to half, and that will be lowering its boiling temperature, and it will be keeping the that fluid, that vapor, longer in form of a vapor, so it will not be going to liquid as it normally would, but in this lower and lower pressure it will remain, and it will be available for these blade rows to extract energy. So they are lowering the pressure, but they are not kind of lowering the temperature after it has finally been cooled. So that is kind of a trick why these all these current turbines used in nuclear power plants and coal power plants, they simply operate with this Carnot's efficiency because they don't lower the exit side pressure by going below the temperatures of then cooling that, continually cooling that liquid. But here's a very powerful woman, strong woman competition winner, I'm sure. So let's see if we have, okay, without to look that yet. So let's go back here, and yes, here I do show that we have been talking about this, having this a heat pipe. It's kind of not necessary to have this, but because all the air that is and remains in a gaseous form, it will behave like that ideal gas. Let's see here. Here it will, all the gaseous gas air will follow this kind of ideal gas volume versus temperature versus pressure curve. So as the temperature goes down, the temperature goes down, the pressure will go down kind of linearly towards the absolute zero. So that is kind of what air does in this kind of a system. It kind of it does not help us to achieve this below a higher efficiency than the Carnot's theorem, but we get that higher efficiency when with this kind of liquid that gets vaporized and then condensed and then cooled below the boiling temperature. So it will be acting this way. So when we have a mixture, so it's a mixture of these partial pressures on both sides. So it needs to be kind of considered. And here is a heretic system. Now, as we have here ideas that we only need to remove 2% of this heat that was put here into in a form of waste heat. We get the useful work, electricity, like 98%. Then we can use this 98% for powering things, and one of those things would be a heat pump. And heat pumps, they are able to cool, they are able to make colder by moving heat from colder to a hotter, but it has a cost. For example, this can operate with, let's say, 50% efficiency. But if you have if you're taking 90% of energy in form of electricity and you use that for powering a heat pump, you will have enough power to cool this exit site, so that you don't need to be moving the heat to an environment in the form of waste heat, but instead you can move it to this side, and you can release it here where it goes back to the turbine. So turbine will be taking energy out of the system, and it will be using part of the system for powering the heat engine. But if it's kind of operating with this, taking 90% and it spends then it would need to be taking that 10% that would be needed to be removed here of this heat. It will then cost maybe 20% to power this, but there will be still most of the energy available that can be removed from here. So this is a totally heretic. Lord Kelvin would be very embarrassed about his conclusions, or maybe I am. But no, this is kind of a next level stuff, so to say. So Lord Kelvin said that this kind of a machine would not be able to be built, but if it's efficient and if it can power heat engine, there were no heat pumps when Lord Kelvin was around. So let's see. And I here have this heretical, half heretic system again in a comparison to current state-of-the-art energy producing machine, which will be cheaper. We assume that both of these can produce 1 megawatts of electricity. And this enormous monster structure windmill system, it will be weighing millions of kilograms. It will be having enormous concrete block here under it, lots of metal, all kinds of enormous things in this. But if we instead use this kind of a much smaller thing that we put to the sea, and we have temperature difference even in lower in layers of sea, whether kind of a surface temperature might be different than the temperature below, or this above the surface of water may be let's say minus degrees, and here we have plus degrees. So there will be a small temperature difference, and we can drive that megawatt or megawatts of heat power um, into this structure. So if we are moving 1 million joules of heat per second into this system, and we can get most of it removed from this system using a generator, then we will be having a generator generating that megawatt of power then from a much smaller structure, and it will be available much more constantly than from the wind turbines that don't work when there's no wind. And in this kind of a system, let's see here. So I assume that we will be heating this liquid at the bottom of this thermosiphon type thing, and we will be having a pump that's kind of circulating some kind of a coolant here. It will be gathering heat from the water. It will be moving it here, and here it kind of releases the heat. Or we can use the heat pipes for transmitting heat into this or many kind of systems. So we have the turbine here, and importantly, we have the pressure difference here. So if we have the pressure difference because we are cooling this side. Initially, we can cool it. We can cool this side. If there's a very cold here above, we can have a heat sink here, and so it will be keeping this side much colder. And as it gets colder, it will be cooling the liquid. And if we keep the liquid here, if we condense it kind of with this kind of a metal system, so it will remain here, and it will be causing the partial pressure drop in this side, and the pressure difference will be powering this turbine. And as the fluid or vapor moves through the turbine, it will be handing over the heat of vaporization here, so that most of it, so that there's only a little bit of energy that needs then be removed from this side to the ambient air. Or if we use this heretic system, that will use a heat pump, and heat pump is powered by electricity generated by the generator, and the heat pump will be cooling this above side. So we will have that pressure difference, and this kind of a thermosiphon can have that megawatts cooling power, and if we get that taken away with the generator, then we can replace these monsters and power our cities with the heat coming from the sea or rivers or other bodies of water, for example. So as I see it, I have found a way to generate electricity from the environment, small temperature differences that exist everywhere. That can be converted with a very high efficiency to electricity. And that electricity can then be used for making hydrogen, ammonia, methane gas, synthetic fuels, and then with this new patent application that shows the technologies that enable us to use those synthetic fuels again with above 90% thermal efficiency. So to me, it looks like this man-made global warming can be greatly eliminated with this kind of technology. Is there anything more that needs to be done for saving the mankind for this global warming thing? Well, let's arrange these energy things first with these inventions. Thank you very much, and I hope you have enjoyed this show.